there's still a lot of unexplored territory. I cannot buy with a nice like 130 kilowatt motor and like 40 kilowatt hours battery. I was what I would like, yeah, a small car, not like small. Well, yes, but in fact, that's gonna. I think that's still gonna be a sedan, but. But I want an active key as my main car. That's what I want. This is my favorite. Yeah. It's going to be a platform much like the Jetta. Yes. That's probably going to make me I can hear that it's already like better. Battery because there's a lot of people out there who want Texas ones. I mean, I'm sure, it'll be on the Tesla store. Yeah. It'll be an option on the Tesla, and you can have it where it's got a little gun. The GM Volt gun rack. Oh yeah, that was hilarious. Maybe antlers. Yeah, Texas Longhorn. The only thing I don't like about the new Ford is the charge. They didn't offer 6.6 kilowatt charge. I know. I wanted that. I was like impatient. How many people have a job where you sit 8, 10 hours? Yeah. You need one place charging. Volts is fine, but you can only set barely 1.9 kilowatts out of that. That's fast. And 20, 30. A lot of people really need more than half of the time. Because I think almost more than half of the charging. Why? Because it's going to be yeah. In fact, as a retro, I was very happy finding my current place. In fact, I didn't even find what I wanted. I found something where I could convert this the 20 amp, 120 volt, and move the neutral over and make it a 240 and 6, 20. Did you discuss what you wanted? No. They don't know this. I mean, like, don't use number 16. Yeah, no, it is 12 gauge. Make sure that it's there, and I can pull 16 amps. Right now, I haven't had a chance to turn on the whole. That's why you just start getting breakers. Yeah. No. I have my own meter in mind, so I can just replace, but I just haven't had a chance to move the breaker.
Let's go. First one.
I'm just taking it
Yeah, I know. I was just listening on the way in.
Yes, they thought charging was
collecting data.
Literally drop in
Kind of a humbling thought.
So I've actually done that. I've done this. What I did actually on mine is actually fit a Brusa charger. Yes, it fits. It feels maybe you did it first, and then you kind of prove that another guy. I forget his name. Yeah, he's got 3 of the water. Yeah, he's got 3 of the water planes. He has his own. He has a separate. He actually got me hacked in. I like the way I did this. You wrote up this description. Yeah, most people do. Yeah, like, what did you do? Like, he's really good. Yeah, I know what he did. Yeah. Having those, he's like, I could have done next job where we have a Tesla or a fire truck or something. But the reality is, like, all the charging stations have been 30 amp 208. So this works fine. Oh, yeah.
No, that's true. It's because it's very using the current sensory reality. It might be.
Yeah, that's why I show the output to the battery and charging on the shoulder. Oh, yes. You know, you don't. Your display is that's not my thing. I think maybe they that's detrimental to the battery life, especially hot and cold.
Yeah, well,
Yes, and oh yeah, like he was here last CGI. Last time it ended up being 2 hours, so this time I'm not going to try. Because they had it did last time. I mean, it was interesting to answer all the questions, but I think it's yes. We changed a little bit. Yeah. Yeah, we did. It was only that. Or no, it was only that's why I have mine as a backup because I'm like.
But I think in Canada, Canadian tracking video.
I'll also give you the slides. Yeah. I just wanted we could hear
And then we're already gonna figure out.
You guys have
no idea. I think that's what my team was. I have to take leave. Oh, now wait for me. You can just use the.
Oh, yeah.
So they uploaded the data stream. Yes. It is
Because I think when I did it.
So I would say,
I don't think that applies.
Good morning. I'd like to try to call this meeting to order. If everyone would like to take a seat, please. Well, you're already sitting, George. Get your coffee, get your snacks, leave a tip, please. Preferably more than 2 cents.
Who did the cartoon?
I found that on the web. Thought it was funny. So,
Okay.
not quite as funny as the cat getting sucked up into the UFO, but I thought that was overdone.
That's fine.
Well, today we have the privilege of Jerry Whaling speaking, but that'll be after my ridiculously long presentation. Mostly what I'm going to be hitting today is what's happening next month, and there's a lot. So let's hit last month. In January, SF Bailey's meeting. If you guys are wondering why I'm talking about SF Bailey's more and off, I know we have a lot of leaf owners, but due to their collaboration with us during World Record, I'm giving to them so that they know we almost like one club, not keeping it separate. So SF Bailey's meeting at the Nissan Research Center, and then our meeting. Fortunately, SF Bailey's loaned us their VW e-Golf person because my plans fell through. February also SF Bailey's meeting there at Macalon Engineering. That's right next door to ChargePoint's headquarters in Campbell. Annual EAA meeting, which we just had, and then to those of you who came, George, thank you, and the rest of the San Jose group to the Best Off-Road Smart Car in B-Class event where we got the test drive. Yeah, we had 5 days, so lots of pie, and we ate almost all of it, which I'm grateful for, because there were 4 or 5 pies. So I hope we can do that again next year, and honestly, if we could have another pie meeting, I wouldn't be disappointed.
it was very appropriate. It was Pie Day.
It was Pie Day. That's what I had the pie shirt and everything on. I celebrate pie. Now we can come back June 28th and have 2 Pie Days.
I think we should do that. Isn't that's Chow Day, right?
Yeah. I don't remember if it's. I can't remember. I think it's the middle of the week. It's either a Saturday or Sunday. I don't remember what it is. Anyways, so in April, lots of fun. Cupertino's birthday is on the 11th, and I already have this up. If you guys want to check, you can go to eaasv.org/Earth Day and see all the sign-up sheets. And they're all. We need at least 5 cars per event, 10 cars for the Mission Fair, Mission College. Ed is pretty much in charge of that. Mission
And we have
College
2
Fair.
right now,
Good.
so we need more.
We need a lot
What
more.
kind do you have?
Everything.
A leaf and a thing.
Okay, cool. So Mission College Eco Fair there on the 23rd. Earth Day, apparently I haven't found anybody who's actually doing anything on Earth Day. Maybe they wanted to leave it alone this year. But the last 4 here, Mission College, Santa Clara, Sunnyvale, and Los Altos, are all right there in a row. Los Altos capping off technically the end of the weekend, Sunday. So Sunnyvale's on Saturday, Santa Clara's on Friday, and Mission's on Thursday. Earth Day being Wednesday.
No conflicts.
Right. They're all, fortunately, I guess they coordinated their schedules, which really helps us. But yeah, the Cupertino Earth Day is going to be much earlier there on the 11th. And I didn't have it in here because I don't get to go, but if you guys have the chance, it's free. The Formula E F1 races down in Long Beach. You gonna go, right, Jeremy?
I can't, I'm on night shift.
Okay, right, well,
Marina's done.
it'll be pretty much all day, a free event. So if you get to downtown Long Beach and see the Formula E races, it'll be on YouTube too, but please go if you can. I know that Paul and Marina are planning on going.
There was an event a couple days ago at.
Yeah, at Computer History Museum about it, right.
The CEO of Formula E Racing gave a presentation, and there was a Formula E car there to see.
Yeah, I saw you guys' pictures, that was really cool.
Where's that Long Beach event you mentioned?
Pardon?
When?
It's
April
on
4th.
April 4th, all day.
April 4th.
It's Saturday. So it's the week before the Cupertino Earth Day, which is what I was going to mention about. So I highly recommend it. Lots of places to stay, like, this is one of the things, just as a side, the Queen Mary 2, I think? It's right across the harbor, and you can stay there, it's a hotel. So
Oh, wow.
it's like 130 a night, so I highly recommend it. I've been there only once, and I really liked it. So yeah, Cupertino Earth Day, and then all these work. So if you guys can check it out, eaasv.org/Earth Day, all one word, and all the sign-up sheets are there for each individual event. And if you need to leave early, or if you have any qualms or questions or anything, please leave them in the comments. I wish I wouldn't put the web page up here because you can't click on it. So,
I've
anyway.
got a small handout in the back on the table for anyone who's interested in coming to Mission, so.
Cool. So that's all I have. And,
Wes, do you not have a button on the website? You got a button for meetings, but you don't
I
have
can
one
put a
for
button.
Monday?
I can put a button, but I tried to make I was deliberately trying to make the URL easy to read and easy to get to. And in fact, if you're willing to go one extra step, each name of the city is furthermore to go directly to it. So I wanted to make it as simple as
Too
possible.
much detail.
Yeah, one button for each.
That's all we can negotiate.
Anyways, so let me welcome Jeremy and his presentation, The Future of the Electric Grid. Get rid of my,
It's dark.
ideally, yes.
It's so bright, I wish it.
Get rid of my thing, because if you don't want to see mine.
No, it's fine.
Yeah, you know everything. Go ahead.
Okay. So I'm here to talk today about the electric grid and basically how I see it transitioning in the future to a renewable future. And first thing is, I have a disclaimer. This presentation is basically just my independent thoughts and sort of analyzing where the future of the grid is going. And it's not a reflection of my employer. I work for the California ISO, so I manage importing power from out of state. And also, I just want to mention technologies and companies mentioned. I'm going to talk about a few different companies and technologies. I don't want to endorse anything as like an investment or anything of that sort. Just kind of like these are companies that are doing things that are, I feel like part of the future. So just kind of for the lawyers and such. So right now the grid is going through a transition. If you haven't heard a lot about that, the utility companies have a reputation of being relatively stable, but not something that they're like a very innovative company. Basically, things have been the same way for 100 years, right? And right now, we're transitioning to renewable energy, but the grid is a living beast that must evolve while it's still being used. It's kind of like you're trying to work on a car while it's still moving. So that is a challenge that is kind of unique. There is a very strong push to use renewable energy. We have renewable portfolio standards set by California, and there's other places in the world like Germany that have that. But there's laws in place that aren't exactly clear how this will be accomplished reliably, especially as we get to higher percentages. We have in California it's 33% by 2020, and they're talking about 50%, and eventually I think we want to go to 100%, right? So there's this push here, but we're not, they just set these goals, but nobody really knows, okay, well, how is that going to be accomplished? And further, we want to keep reliability as priority number one. So the grid today can kind of be thought of a upside down pyramid. You have utility scale generation, You have transmission that brings that power to areas of load. You have distribution that distributes out the power to the customers. And then finally, of course, you have the customers. And you have power flow generally in one direction. You know, this is kind of like an example grid here. You have a generating station that's typically located far from load, and transmission lines are bring it to the load, and of course the power flow. And you also have customers that do what they feel like, mostly, right? They just use the power, they turn on the lights, they turn on the air conditioner, and they don't really care. This room may be an exception, but a lot of people don't really care about electricity unless it's not there. Right. So we're kind of transitioning now to this grid of tomorrow, and this is kind of the block diagram of how I see that happening. You still have utility scale generation. You have controlled transmission that is better to handle different generation from different areas and bringing it to different people. You have bidirectional distribution that both takes power and brings it to people, and takes power from customers and brings it to other customers. Further, you have interactive customers that do mostly what they feel like. They do interact with the grid. They do understand the consequences of how they use power. You have customer storage, and you have customer generation, like solar, mostly solar for customer generation. And I changed the shape from that pyramid to a sort of trapezoid because the customer before would do what they want, and just kind of it's moving around a lot, or the load varies quite a bit during the day. We'll talk about that. But the future, you have a stability caused by both customers' generation that provides for a lot of the customer's load, but you also have that customer storage, which can help with the changing load that they have throughout the day. So this is kind of the block diagram. You still have transmission that is flowing mostly one direction. You have a distribution power flow that is you have secondary customers like houses that can feed out, and you have primary customers that are taking in at different times. And so your distribution grid is going to be quite dynamic. So what we'll do now is I'm going to go through just the different portions of this trapezoid, and I have a few slides after that as well. So for utility scale generation, we still have traditional units, but in the future, a lot of this, what I call transitional fossil fuel units, they're actually a combustion turbine, which is kind of like a jet engine, with a combined cycle. So they're actually using the waste heat from the generator to run a steam turbine. So you're actually kind of getting a dual stage out of the plant. And it's kind of, I like to think of it as the Prius of the power plant world, because it's actually very efficient. And the really important part of it is it's very flexible. So you usually will have, I have a little diagram here. You'll have like one combustion turbine feeding, you can have like one combustion turbine feeding a steam plant, or you can have two combustion turbines feeding a plant, or something like, say if you want on a Sunday, your loads are going to be very high, you'll just run the combustion turbine for the peak. So these plants, they're very flexible and they're efficient, and they can start and stop pretty quickly, and they can ramp quickly, which is very important for chasing renewable power. So we also, I'm sorry?
Is that what they call a peaker plant?
Usually a peaker plant is for just the combustion turbine. So the traditional peaker is just the gas turbine that's up there. But nowadays they're actually working on some of the peaker plants. They actually have been adding to the plant and adding the steam turbine portion of it. So, but with nuclear, we have an existing large unit in the area. We have Diablo Canyon, but there is potential for smaller and more advanced reactors. I'm not going to go really into the technology. There's a bunch of different promising technologies. But unfortunately, politics will kind of decide this sector. With the chuckling. Because there's a lot of people that, some have good reasons for reasoning that we don't need this. But I think there is a lot of potential there. And I hope it is explored more than just, a lab scale. But So that portion, it's very unclear whether that'll actually be developed here, but renewables, which lately has just been large-scale photovoltaic. We do have thermal solar. There's lots of wind, lots of hydroelectric, geothermal, biomass, and biogas. The key here is there's a lot of different sources. In the future, it's going to be dominated by solar in this area. Basically, whichever area, outside of California, if you have a large wind resource, the grid is going to be dominated by whatever renewable resource, like wind or solar or both, that is in that area. And again, units are typically still far from load. A lot of these renewable plants even, they're built in the desert. Wind parks are built in mountain passes. You still need transmission to bring these sources of power to us. And especially with things like hydroelectric, you can't move the dam, you can't move the river. So you need to be able to bring that to the areas of load. So when I talk about like these lines that bring these power, most transmission lines, which usually is like 500 kV, 500,000 volts, 230,000 volts, 138,000. Most of that, they actually control the power flows using generation. They basically have like a effectiveness factor of where the generator is located. And so sometimes you're moving up and down generators, not because of changing load patterns, but because of changing like conditions on the grid. So line ratings are actually, they're not thermally rated. They're not rated by their ability to carry lots of power and not overheat. They're actually, sometimes they're rated by stability or by voltage. So this can actually lead to inefficient use of assets because you're trying to move these generators around to manage the stability and voltage ratings, but you can't really, just maximize their use to actually transfer power. And also new lines are really expensive. It's pretty hard to find like costs of every single line, but looking at like transmission and stuff like that, and I've read through a few papers, it's on the order of $500,000 per mile. And that includes like the permitting, the environmental studies, and and adding, actually running the lines and putting in the towers, and it can be pretty expensive. So basically, we need new ways of controlling the power flow over these lines without adjusting generation, because your generators are going to be moving around to match the load and the renewables, and you can try to do both, and that's what we do now, but you're going to hit a limit, and it's going to get harder and harder and harder to do that, especially cost effectively, and just you want to minimize the use of renewables. I'm sorry, minimize the use of combustion turbines or net fossil fuels. And you want to extract the most renewable power, and you want to do that reliably. So there's a few different technologies that allow this, and I'll be talking about it now. There's phase shifting transformers. There's a company called SmartWire, and we'll talk about that type of technology. There's also DC links, system protection schemes, and then of course interactive customers, which we'll get to as well. So for a phase shifting transformer, this kind of is a little bit technical. There's the power theory and stuff that allows this is you use two separate transformers, a delta and a Y, to take a 90-degree copy of the voltage and inject it slightly out of phase back into the line, and this actually allows you to adjust the power flow. I won't go into the technical side of how that works, and it's actually, I've been looking at how to explain that quickly, and it's pretty difficult. But basically, you can just think of the AC power transfer as proportional to the difference in phase angle. And so once you're able to change the phase angle with these pair of transformers, you're able to change the power flow over the line. And if you have like two lines in parallel, this is just a simple example, you can actually just change the taps and be able to change the power flow over a pair of lines. So in the existing grid, we have phase shifting transformers in the western interconnection, the portion of the western United States that's connected together. And that's actually usually used to control loop flows, so flows over the eastern and western parts of the western interconnection. And they're huge. They're giant transformers that do this. So there are smaller versions, and they may be considered in the future. We're just looking at putting more in the interconnection to handle loop flows, because that may increase as well. But there is a technology called SmartWire that actually kind of does the same thing, but you don't have to have the giant transformer. The actual the component that does it is actually located along the line, and it's SmartWire is a company that makes this product. It's actually a family of solutions called DFAX. It's distributed flexible AC transmission system components, and it allows you to change line flows without having large amounts of equipment at a substation. It actually uses series reactors that are placed along the power line. I actually have a little diagram. This is an older design. There's some newer designs that do away with the DC capacitor due to life. But basically, you're using a controllable inductor and you're inducing more current or less current to flow slightly out of phase. So that way you can control the line flows. And these are actually, they're located along lines. There's like maybe 60 to 100 along the line. And they just kind of snap on to the line. And it's actually a very easy upgrade, and they communicate back to the mothership, and you can control the line flows quite easily. It's actually a really promising technology. There's Tennessee Valley Authority is doing some pilot projects with it, and from what I've read, they are like 2 thumbs up, awesome, this is really cool. I've been trying to find a lot more information about this technology, and it's kind of, SmartWire doesn't put a lot of their like, they don't have a technical PowerPoint that goes through like theory. There is the university like documents on it, but it's pretty theory thick. And so, yes.
So what is it, the purpose of it is to like slow down the flow of power? Or
yeah, so you can do adjusting power flow. So you can change it from like, if you have like lines in parallel, this is a very simple example, but you can have basically weaker lines that are in parallel with longer lines, especially during outages. So you want to be able to control power flows so that way you don't overload any single line or cause any sort of problem that way. So it's similar to a phase shifting transformer where you can take something where you would have 50 megawatts on each line, but say each line was not rated at 50 megawatts, one line was weaker than the other. So you actually have to dial back the power on that one. So it's very key that we have the ability to control power flows along these lines, connecting areas of load without adjusting the generation, because you may not be able to adjust the generation in the future.
So is that ISO does the control of this, or is it done on the line?
It would probably be done either by the utility or by us, yeah, in the theory. But one more question, I gotta keep going.
Okay, I'm sorry, go ahead.
Okay, I'll keep going. From what I found, the maximum line voltage, there's some that it's hard to find what the maximum voltage, but a lot of this stuff has been kind of like on the sub-transmission and distribution. So yeah, I think because it's easier to design for, there's things like the lightning, there's like standards for lightning and for weather and stuff like that, that maybe it's easier to design for distribution. I haven't really quite found why they haven't tried it at like the highest voltages, because it seems like it would be more lucrative to do it at the higher voltages. But if it starts on sub-transmission, that's okay. We could definitely use it everywhere. So if they can evolve it to transmission later, which it seems like that's completely possible, then it's going to be a very good technology for us. So, because in the past, I mean, forever, it's always been about adjusting generators to get around these line limitations, and to have something that can adjust it is just so mind-blowing for the industry. But there's other technologies and that sometimes will be used for like pockets of load. One of them is DC links. So to have a DC power link between 2 areas is very useful, where you have like a very high population density, and you need to be able to give that area power and be able to adjust it without having to use a ton of AC lines. And the way this sort of is worked out is high voltage DC has actually been used in the past to cover big distances. So there's actually 2 in the West that we use. We have, there's one that runs from near Oregon and Washington all the way down to Silmar, and that carries hydroelectric power up from BPA area down to Los Angeles. And then we also have one that goes from Utah to Los Angeles that brings power from out there. And the reason why DC is used there is because the conductor cost is lower, and it actually ends up paying for the converting stations on either end. So, and usually converting stations are quite expensive. So it's been used in the past just for long distances. But it always has the secondary advantage of you can adjust the inverter to the power output that you need. And they actually have used little converting stations back to back to link interconnections between the West, the East, and Texas actually has their own interconnection. Because the frequency difference over that length of wires, we actually can't do that. So they actually just have DC back to back. But in the future, we really need DC links that will be over shorter distance because we really need this secondary advantage of being able to adjust the power flow. And the first one of this kind of example that I've seen locally is actually there's a cable that links San Francisco with East Bay. It's called Transbay Cable. There's a company that actually manages it. And it runs 53 miles. It's not a straight shot across the bay. It actually goes all the way from Pittsburgh. So it's up across the bay and it goes all the way over to San Francisco. And this is kind of the reason why they built this is because San Francisco has slowly been removing their power plants from the peninsula. And they've been adding power lines to make up for it. But at some point, you just start having this kind of spaghetti of power lines and you end up leaning towards more of like a cascading failure if you have one of these lines go out and such. So, I mean, reliability isn't, we haven't had any problems with that, but you start looking at, okay, well, we need something that can provide like a generator to San Francisco so that way they can have power that's just right there for them because they're quite a large load. 400 megawatts is like the size of a good sized power plant. So to have this where they can easily dial in the power is really a big deal. So that's in the future. I think we're going to see more of these. This is 400 megawatts, and I think it's 400 kilovolts DC.
400.
Yeah. So the next
400 kilovolts in the DC? How much is 400,000?
400,000 volts. Yeah.
That's 1,000 amps.
Yeah, 1,000 amps cable. Yeah. Well, I mean, a lot of the DC is usually used like it's for the one that runs from Oregon all the way down to LA is 500,000 plus and 500,000 minus, so it's 1,000,000 volts technically, but it's centered ground, so that we don't need to have crazy insulators. So high voltage DC usually means really high voltage for that kind of stuff. Yeah, I mean even the voltages for transmission lines, they go up to 500,000 volts, 230,000 volts. It's all about reducing the current, so you can reduce the current conductor size. So
Current to 1,000.
yeah, I mean there's lines that run 1,000 amps normally. So yeah, it's quite humbling when you see the actual figures of some of this power. But continuing on, we got the one thing that we do have a lot of already are special protection schemes, SPSs, or they're also called remedial action schemes or RASs. And they're designed to detect sort of like abnormal or predetermined, like this is not a good condition for the system to be in. And what it is it's kind of like an automated operator. It will start making decisions and changing lines or changing generation or load because it needs to be able to be done very, very fast. So speed is important because cascading outages, when you have a transient instability, we're talking on the order of cycles. So if you have something that causes that sort of instability, you need to be able to take corrective action like, really, really fast. So these are already kind of common, but you're going to see more of them. And unfortunately, it won't be something the public really ever sees. It's just really a computer deciding, commands. But it does include like allowing for higher power flow over a set of lines, so that way you don't have cascading outages. Like a common SPS will be if you have like a generator and you've got a set of lines, but you just lost like one of the lines or two of the lines, they can actually turn off that generator really fast because you're going to overload that other line really quickly. So it's just another system that allows more power flow, helps balance and load generation. If you lose a large amount of generation very quickly, you need to be able to remove load very quickly because you need to keep that balance in step. So if you lose like 1,000 megawatts or something in certain areas, there's actual like schemes to either change load, like a pump load or other stuff like that, or they actually start, adjusting the lines and stuff like that. So it does increase overall system reliability. It's something that's just going to continue to increase.
Will this help with avoiding power outage similar to the one that happened Midwest all the way across to the East Coast?
Yes, because you can start taking lines out of service earlier, or you could start changing your switching patterns earlier. They're really, unfortunately with SPS and stuff, they're very specific to the area. So there's a lot of studies done by the engineering sides of utilities to understand what conditions these happen under. There's a lot of simulation done. So it kind of like, I can't say it will prevent that because there's a lot of stuff that leads up to that, but it does, I mean, anything that increases system reliability is usually a good thing. So there's a lot of different ways of helping prevent that. So, but now that we've talked about transmission and how we can control it better, let's talk a little bit about the distribution, how this bidirectional distribution will sort of happen. Basically, residential areas will probably become self-supporting or start exporting power during the daylight hours. Assuming normal, right now, time of use and net metering rates, the encouragement is sort of to use power late at night and to export it during the day. So you're going to have things where that area will actually be exporting power, but the demand will increase during the night if you have things more like customer storage or EVs. And even if net metering sort of starts sunsetting or going away over long term, you'll have things where the residential just won't take power during the day and they'll be charging their own storage, and then they may take it at night only for cheaper power then. But commercial and industrial load is really focused on reducing demand fees and increasing their efficiency. So they're trying to reduce their load both in the spikiness of their load, because a lot of things like if you have air conditioner units, and you've got a big plant and you've got like 3 big units and they all try to start at once, your demand fee is going to be incredibly high, and it's for the month. So they were working on like either changing the order of how they turn on their air conditioning or having storage there. But also you're looking at, well, workplace charging may increase your daytime load. So they actually may end up having it where residential areas will feed out to commercial and industrial where they'll charge customer EVs. We're going to talk a little bit more about like loading and what it means to have a lot of solar and stuff like that. But basically commercial is all about reducing their costs to the utility. So increasing their efficiency and reducing demand fees is going to be a really big deal. The only thing I also note here is downtown areas, like very urban areas, like San Francisco and stuff, they're just the density of people and the density of the workplace there. Just, I mean, you have buildings that have megawatt loads, and you just can't have enough renewable energy on the building or on the roof to be able to manage them. So they will still have a grid and will still have similar flows to what they have now until customer storage is more widespread. So if they start getting more storage, then you can see things like they'll start working with the load curves to be able to counteract, excessive renewables, and we'll get into that too. But basically, downtown areas are going to remain the same for quite some time.
Will the residential pole-top transformers be able to handle the reverse flow?
Yeah, I mean they're rated. They should be able to handle the reverse flow. You do have issues with if you're pushing out a lot of power during the day and then you're pulling a lot of power during night and you're causing excessive heat in the unit. You could have a shortened lifespan of the unit, but usually utilities, they're working with you when it comes to putting in your solar, because you have to do a utility study. So they do look at that, and you tell them, hey, I have an EV. They'll upgrade you if they know that transformer is just not going to be able to handle it. But that is a concern, is excess late night load where normally the transformers would cool down is no longer there. That eventually you'll look towards replacing more of the marginal transformers, and I think over time it'll be gradual enough that you won't have just suddenly needing thousands of new transformers, but it will be something utilities will have to look at. So, but yes.
Quick comment on the transformers. They typically have a 50-year lifespan, and insulation materials and dielectrics that they use for cooling and stuff have improved massively since the 1940s when they designed this stuff. They don't use mineral oil anymore. So the incidence of failed transformers is going downhill. This is just a scare tactic from utilities saying, oh, we got a huge
Yeah.
transformer bill coming up ahead.
Well, I mean, there's people that have been in the utility industry for a long time, so they know about past transformers, and there's a lot of equipment that's older.
Really?
But there is, the newer transformers, not only are they built with better materials, but they're also more efficient. They have special steel that they use in the core that is, the magnetics of it mean that less is lost in the eddy currents and stuff, the things that basically heat up the transformer in the first place. So you're looking towards more efficient transformers over time.
They're going from 99 to 99.5%
Okay,
efficiency.
so we're gonna keep going. So, and this kind of leads right into this. So you have this development of resources. This slide is kind of like well, it's kind of common sense, but it bears repeating. Planning and permitting and construction of these resources takes a lot of money, and sometimes it takes years, especially for lines and stuff. So, and we also still need the traditional generation and adequate transmission for reliability. We still have to provide for the load, even if the sun isn't, there's clouds or whatnot, And customer generation and interaction will help reduce the need for new resources. We're going to go over stuff that has to do with how the new resources or why it will help. But it's kind of, it bears repeating that we still need the traditional stuff, and we still have to have adequate reliability, but we still also have a long lead time on some of this stuff. So there are some solutions here with like interactive customers. I'm sure you guys have heard about the Flex Alerts program and stuff like that, where there's a public appeal for reducing demand. So that's part of the do what we mostly feel like, because it actually does work. And sometimes all you need is a couple percent, because load is, overall the load is high, and if you could reduce by 500 megawatts, that's the top load is like 45,000. So it's a very small percentage, but it still makes a big difference. So the mostly feel like you'll get customers that don't want to, but if you get a few that do, that's going to be really important. And the Flex Alert system, really, if we can have more like smartphone apps where not only will tell you, hey, we could use your reduction in load today, and if you guys have heard of OhmConnect, they're working really well on that to basically have an interactive program. You get credits and you do all this kind of cool stuff to help reduce, and it's kind of like a game, and if it's a game and people think it's fun, then it's going to have better support than things people think is a burden, right? So if we have better smartphone apps, and I actually think a little display, like a little, just a display for the fridge that shows your current output of what you're using. Does anybody here have a TED system or anything like that? There's a few, yeah. Being able to see your load and see your impact, regardless of whether you're a greenie or if you just are interested in the data. Once you are able to see your impact, I think people will kind of go, oh, okay, I see that the air conditioner uses quite a bit of power. Do I really need to run it right now? People come a little bit more thrifty, I think, especially with reducing vampire load. I'm sure there's people that have gone around with kilowatt meters that are able to say, hey, this TV, even when it's off, it's using like 20 watts. Like, what the heck? So yeah, you were saying?
There's a company called Internoc in Boston that does that for commercial customers.
Okay, so there's commercial use again. They're
able to give the commercial customers basically a window on their computer saying you're using too much, you're using too little, you can do this.
There you go. Money. Yeah. So there's solutions for as well as home use. This presentation is a little biased towards home use, but there's commercial use too, where they basically are looking at their demand fees and their load and looking at see how they can reduce, because they want to reduce their cost. But there is,
if you want to play that game right now, OhmConnect actually does stuff like that for demand reduction. So I get texts every now and then.
There you go.
Hey, we're in a high peak load, let us turn off something, or you can turn off something for the next hour.
Yeah, and then you go, well, especially if you had that OhmConnect, not only for just hey, saving money, but for your car and stuff. I know Juicebox is working on a system where you're trying to, they adjust your charging output to match renewable sources. So, hey, you're using more renewables instead of non-renewables. So even if it's, a small amount, it still can make a big impact on the grid when you have so many people on it. So the other thing I want to mention here is not only do we have an appeal to reduce, the Flex Alerts and getting the text and all that stuff, but eventually you're gonna have things where you actually want to appeal to use electricity, where you want, because you have like, and this is especially true for wind, you have a wind tends to peak at night and you don't have as much load at night. So if you have like electric cars charging, that's really good. But then if you have like a solid wind day and you've got solar in the middle of the day, or what, you know, you actually will have times where we want to increase demand. And I put that in there and I think it's really good to have a way to increase demand. But then people go, well, you're asking me to use more so you can charge me more. And it's going to be spun the wrong way sometimes. And it's going to be tough to be able to do that in a way that doesn't, you know, make people mad. I mean, there is stuff like Texas has like a nighttime, like free electricity after night. I don't think free will work out very well for utilities here. Just the mentality, they don't want to do that. But, you know, some way to increase demand without really causing a huge customer burden in terms of their cost.
Right, well, you have all these EVs that need to charge at night. We don't care when they charge, so charge them when it's convenient.
So I think EVs, I'll talk more about how EVs will play into this in the next slide, but that will be something that will be looked at is how do we increase the demand? No, because unfortunately not everybody owns an EV yet, but looking towards increasing demand when renewables are the highest.
Well, one thing also, appeal to reduce electricity.
But yeah, that's the first one.
Well, yeah, but remember, we're getting to the point now where customers are going to be once bitten, twice shy. And
Yes.
like when we were forced to reduce for droughts,
Yes.
and they upped our fees 30%. I don't want to reduce electricity if they're going to start upping it 30% for electricity.
Exactly. So, but overall, and we'll talk more about like where we'll have overgeneration. I have some slides on that. We'll talk about that. But there will be a time where we do want to increase demand, so that way we can get the most renewable. You know, we can utilize the renewable energy the most. Last question, and then we'll move on.
Yeah, well, it seems to me for utilities in California to work this out correctly is something that they, in a sense, haven't yet done.
Exactly.
For what we've got going on now. Obviously, you're not looking to increase demand, but in terms of the relationship, for example, which I'm sure affects a lot of people here, between the fact they have an electric car and they have solar, and the rate structures don't
Yes.
work right.
Yes.
To incentivize both.
Yeah.
For understandable reasons from the utility point of view, but not from our.
Right. So that's why, I mean, that's part of why this is the future, the transition part of the electric grid, right? Because this is something that's like, well, we're going to need it, but we don't know how to do it yet. So, but we'll talk more about like the whole piece a little bit. I don't like to talk pricing, but we will talk a little bit about how the utilities are kind of moving with the increased demand or not, kind of moving forward with, you know, the way they need it on their side and the way they're presenting it to the customer. We'll talk about that. Yeah. But again, with commercial customers, we did talk a little bit about they have their interactive tools too, but looking to utilize battery storage to reduce demand fees, I think will become a really big product. If you've heard of Coda, they're working, you know, Coda, the car company is no longer, but Coda, the energy company, is making batteries and storage systems. And I think also, which I haven't quite seen a lot of, is like, you have a lot of these commercial customers that have a lead acid pack for their UPS installation. Some of them are quite large, but they have this big battery room and they have the high voltage inverter and all that stuff to be able to power their building. What about switching from lead acid to lithium ion to be able to have storage and have it be a little more cost effective? Because you don't want to have to reinvent the wheel and install inverters and all that stuff if you already kind of have that equipment. I mean, I'm not exactly sure what the UPS installations. I'm sure there's things like, you know, the inverter's only rated to run for a certain amount of time or something, or, you know, very dependent upon their, you know, what they have as their system. But I think that would actually be a very good way to go, because lithium ion is very energy dense and it doesn't care about where it kind of sits SOC wise relatively. Like, it doesn't like to sit at full all the time, which is actually the opposite of lead acid. But you can move it around and not have a lot of issue with it. With lead acid, you always want to keep it fully charged, but with lithium, you can move it around quite a bit, and that's a really big deal. As long as you had enough to be able to, you know, if you were discharging into the grid and then all of a sudden had a power outage, it's pretty bad. So you have to have a minimum run time that would be your floor, but you would be able to use your system that was for backup before, it actually helped reduce demand fees. I haven't really seen anything on that. I think there's a possibility there. And finally, I think with a lot of course, EV drivers here, as you start driving an electric car, you kind of learn what a kilowatt hour really is, and you start looking at your electric bill a little bit more and analyzing sort of that way. So as we get more electric car drivers, you start looking, well, they kind of have a little bit more insight into what electrical usage really is. So that's usually a really good thing for being an interactive customer. So, and of course now, talk a little bit more about electric cars. EVs lead easily to demand response. I'll tell you that right now, because they all have J1772, and that protocol allows for the pilot to be adjusted like within seconds. So to be able to change the pilot, bring down charging or bring on charging faster is just like a very easy thing to do. All you need is a smart station to be able to do that. And I know Juicebox is working on that. I think there's some other there's some other pilots on that. But the only thing I know here is, because I'm an EV driver too, and you don't want to do it at public charging stations because a lot of times those are being used for a certain time frame. So as long as your charging time is not critical, I think even at a home usage, you need an override button, and there may be, like a financial, hey, you got to pay $1 or something, or some way to note that, hey, this isn't the best, but you have to be able to charge when you need to. So having a home charging station, if you're in that kind of program, to be able to undo that for the time temporary. Yes?
It can work in public stations too. ChargePoint always said that their ability to manage all of that could mean that, maybe I'm getting cheaper power because I may or may not get it if they decide to drop it for demand reduction.
Yeah, so something like workplace charging would be perfect. But I would consider that public, because that's, a workplace may have public stations for public use, but when you're a worker, I consider that workplace charging, and that's a little bit different. And you could have even public stations have an emergency demand response. The grid frequency is decaying. You want to try and arrest that as fast as possible. So you could have charging stations, but I wouldn't consider that normal demand response. That'd be like an emergency load shedding, which is kind of a different program. Yes?
Can I just confirm that this demand response thing, whether it's level 1 or level 2, or?
Well, as long as you have
sufficient level numbers of level 1.
Yeah. Well, the problem with level 1 is if you have people bringing their cord set, and then you have there's no pilot, there's no signal from the grid. It's just a brick. So you're not going to have an easy. If the station itself has to be smart. So there are ways of having it done on the car with CarWings or with any of the other different auto manufacturers, but then you're getting the auto manufacturers involved, and sometimes I don't think that they are really.
Presumably, if you have 100 spots of the workplace that are level 1, they could buy.
As long as you have, because like I know San Diego Central. Yes, and I know San Diego Gas and Electric actually has like their own little pilot program for it that they do it on more of a cost basis, but they do it with level 1 because it's still a pilot signal. It's still a station that's there, and you're not using your own cord set. But it's slow, but it allows for people to plug in all day and not have to move. So it's a lot more stations, but they're slower. Yes.
Jeremy, the concept of using your own cord set is going to be falling away because level 1 J plugs are available for relatively cheap, and they'll probably be the preferred thing to put in instead of GFCI all along the back.
People don't want to have to bring their cord set out of the trunk, I think.
Yeah,
I find it's even more pain in the butt. I don't know about you guys, but
especially in the rain.
Yeah, especially in the rain. Well, then you have to, the cord gets all wet and dirty. I mean, the focus, I'll just mention this here and then we'll move on to the other grid. But with electric cars and stuff, we're trying to make this kind of like grandma proof. She wants to be able to just plug in and not worry and not have to deal with a dirty cord or trying to pull a cord out of the tangle in the back and stuff. So sometimes I think, we need to, the stations need to be easy and seamless and not have outlets. I know that there are some that have used outlets and stuff, but I think you're right. I think in the end, for safety and for just ease of use, you're always going to have the station where you just take the cord and plug it in. So, the plug itself is meant to be connected and disconnected a lot. There has been issues where workplaces have put in level 1 and they just put an outlet in, and then the outlet wears out really fast because it's not meant to be disconnected every day, twice a day, or whatever. So, but anyway, we'll move on here to vehicle to grid. I think vehicle to grid is perfect for home use for that 6 to 10 p.m. load reduction. in the evening, because you come home, and if you have a car that, say you have a 200-mile range car, but your commute's like 20 miles, and you know that you'll always have excess, like excess in excess in terms. There's people that are like, oh, I want to be able to go home and then drive and, you know, be able to do stuff in the afternoon. Well, if you have a 200-mile range EV, and when you say go drive somewhere and it's only 20 miles and you still have 150 something miles left in the tank, you know, a house usage is actually quite a bit lower than a car. So you can have something that's like 5 kilowatts or 10 kilowatts, which trying to use 10 kilowatts to go down the road, you're not going to go very fast. But for a house, that's plenty, you know, unless you got a mansion. But I think this will also be really big for people that have a low mileage commute or a low mileage kind of like lease or whatever, because you do have calendar losses with batteries, and you bought a car that you aren't getting necessarily the best financial return on. I know they're not an investment in a way, but it's something that, you know, there's people that go, well, I want a 200-mile range EV, but they make a 200-mile trip like twice a year. You know, so you have this, and there's a big demand for big range, but you know, I think there's people that legitimately need that range, but then there's also people that just think they do, and they really need 150 or 100 or sometimes 50, and they kind of don't really figure that out until either they start driving an EV or they start driving a plug-in hybrid, and they realize how little they actually burn gas in the plug-in hybrid, or the Leaf. They buy it as a second car, and it turns out to be the primary car because driving electric is way better than gas. So they realize, like, if I buy a 200-mile range EV, it's going to cost X amount, and I'm only going to use the battery for its full capacity for very little. So I think that vehicle to grid may be a thing that it's like, it justifies the purchase of such a big pack, but then you have things like you're able to produce power for the house at night and then charge in the middle of the night where it's cheapest. So and there's been pilots on vehicle to grid, but there's been here and there about just emergency power systems like Leaf to Home, and there's I hate to say it, but the fuel cell. Toyota Mirai has a Chatham port, but it's only for exporting. So they're looking at but it's kind of like just for emergency. And so we really need to start thinking about, well, how do we do vehicle to grid? How's that going to work? There's different ways. You know, you could have an AC inverter in the car, or you could do it with DC with an external inverter. And it's kind of unclear about whether they want to do, like, because you have to do UL listing and all kinds of sorts of things to be able to export power, you know, as a grid tie inverter, or do you want to have an external grid tie inverter and not have the auto manufacturer work on it? So there's things like that are kind of, you know, how's this going to work out? But I hope in the end that it does in a way that's seamless for the consumer, because there's a lot of people that want that crazy range, but they're really not going to use all of it. And you want to be able to maximize the use of a car and have it be able to power your house, or even emergency power only. It's still pretty awesome.
Well, it's kind of like when you buy solar, you need to buy a grid type solar or down to storage pack.
Yeah.
Well, if I have a vehicle that does it, there's my storage pack right there with
Exactly.
my solar.
Yeah.
And I get dual use out of it because now I can drive with it too.
Yeah, although if you have a normal work schedule, you're going to be having a car at work and not at the solar. So there was challenges. We're actually that's perfect transition to the customer storage. So we'll talk about some about those now. I think customer storage, I'll talk first about like sort of like electrical storage, but there's also thermal storage. We'll talk about that next slide. But the main thing for customer storage is you're kind of are you looking at almost like a used pack or a new pack? There'll be things where we have unfortunately, I have a Nissan Leaf that has a major battery degradation, but that battery for a home use has got tons of energy available and still very high specific power. I can get 80 kilowatts out of my Leaf pack still, even though its capacity is not so great. And that high specific power is really good for mitigating demand fees. So maybe something where, there's maybe a company that takes these spent packs and puts it in a system that allows it towards going to a commercial customer. And I know Tesla has been talking about doing that, and they don't really make it clear whether it's a new pack or a used pack. I imagine there's probably some that are used packs, and they probably
They're new. They're building these things that look like big, like stationary transformers that are like.
They're all new? Okay.
Just like 6.5 feet tall. I mean, someday maybe they may.
They may be used. I mean, it's the same cells, right?
I'll beg
No,
to
they're not.
differ.
They're too
They're
low
not
power.
new packs.
They're not new packs. Okay, so I'm here new. I'm
Spec
getting
ones
used.
with blown contactors like my own.
Yeah, so, oh, the contact bill, sorry.
So what's actually they're new because they're using lower density.
Cells.
Yeah.
Well, I think that's kind of why I put both spent and new, because there's reasons to have both, because this spent pack's like, I mean, how many people here are retired? We got quite a, or almost retirees, and like, I certainly wouldn't call you end of life, right? You're still here, right? So they should be called retired packs, because they have a whole nother life after the car, because the grid use of these packs is like an order of magnitude lower in terms of power and energy density needed than in the car.
Actually, it only costs you the core charge in the
Yeah,
battery. So
yeah, I
you
mean,
keep it.
Yeah, exactly. Like because Nissan's core charge, I think it's like $1,000.
$1,000.
Yeah, $1,000 for a, mine's like 16 kilowatt hours. Hey, that's a pretty inexpensive pack. And 16 kilowatt hours, I don't know how many people analyze your bill, but mine, I averaged like 7 or 8 a day, and that's so 2 days worth of storage. That's pretty cool, that to be able to use that. So I think spent EV packs will have a place, and new packs will have a place. And I think with new packs, you're looking at things like, well, they need more kilowatt hours in a small space, or they need to be able to do really high demand fee mitigation, or they basically need to stretch the pack more. So you need to be able to handle, that kind of power levels or the energy levels for whatever reason. And that's kind of what we're seeing on the utility side. Is the utility is actually, there is some CPUC things on storage, and they have, it's probably going to be new packs. I mean, I know there's Edison has one it is all new battery packs. But I think for customers, spent packs will actually be a pretty good deal. So, but the new battery packs may actually have wheels and a horn and a steering wheel, and they may be the EVs themselves, which we were talking about earlier with vehicle to grid. Again, with this, I kind of just present all kind of the facets as I see it for the electrical storage side, because it kind of depends on like the economics and how long do the spent packs last. Like if there's some sort of going off the cliff moment for these packs, but I know there's a few people that have run their Nissan Leafs past the warranty stage in their cars, and I guess they're still doing like they were okay, if the power levels were low. So I'm thinking that the storage for EV packs may actually be they might do quite well and live quite a long time in their retirement age, right? So, but there's actually, besides customer storage on the electrical side, there's also thermal storage. So you're looking at cold storage or hot storage. So in California, it's mostly about cold storage, unless you're talking about a thermal solar plant. But this is actually becoming quite common at universities and large commercial entities. They're actually freezing ice or freezing water to make ice, and then running water through it during the day to run their air conditioning system. And I know the California ISO does have one. Their main facility is a LEED Platinum building, so it's got all kinds of fun stuff for that. And they actually run it mostly in the summer, because that's when it's most economical. I'm not exactly sure about other ones, whether it's economical to even run it in the winter. But I think it'll just become something it's existing, and it'll become more widespread and possibly scale down to smaller levels. Don't know if it'll go to the house level though, because when you have something that's started, it's not solid state. It's going to have maintenance and stuff with it. You're going to have air conditioner that's you're now trying to run chilled lines and stuff. It's quite different than normal home usage. So I think customer storage when it comes to the house will actually be more electrical than any sort of storing air conditioner. And when it comes to cold, actually with hot, there is customer storage already. I'll talk about that in a second here, but you can store heat in brick, in molten salt, and hot water with a hot water heater also, obviously. But actually in colder European countries, if you've ever been to like the UK, they actually have this thing called a storage heater. And so they have like this brick that they can heat it up a lot at night, and then it slowly gives off its heat during the day. And they actually, if you go on Wikipedia and you start looking at like the UK grid, they have mechanical time of use meters, which is kind of cool. And so they've been doing kind of this stuff for a long time, because I won't go too deep in the history of the UK, but they actually didn't have gas service for a long time until they found the North Sea gas. It's so they had a lot of electric heating, and so that's how they kind of solved the storage problem for them, is they were able to run it essentially at night. And a lot of the thermal storage, like with molten salts and doing stuff like that, that's actually been really researched in the Scandinavian area and stuff like that. They, you know, it gets really cold there. So like they are really interested in keeping the heat as long as possible and stuff like that. So for California stuff, it's been mostly about cold storage and air conditioner usage.
Whereabouts is this California ISO building?
That's in Folsom.
Oh.
So yeah, east of Sacramento. So.
Are there public tours?
They do. If you go on their website and request one, they will show you there's an overlook where you can actually see operators like myself doing their job. Well, right? Mostly. They're good. You know, 24 hours a day.
They have similar office in SoCal?
Yes, there's a similar, we have a hot backup facility. We run a lot of the southern stuff down in the southern location. And yeah, so we also serve as a backup facility, have the ability to staff fully in case of emergency. There's certain grid standards that require a backup facility, and some don't require that you need a full-time, but we actually have a full-time 24-hour backup facility that's available. So, and that is staffed. So anyway, but start talking a little bit about customer generation. Of course, this, at least in California, you're talking mostly about solar. I think there's a lot of people, you know, utility mindset that's trying to fight this, but you got to start assuming that any customer that can put up solar, they have a roof that is able to see the sun, doesn't have trees blocking it, eventually they're going to put up solar. That's going to happen over the next 20 years. That needs to be just like, hey, this is the way it's going to go. Because you start looking at things like rates that are going up and stuff, or people that just kind of sort of wake up and realize that their bill is really high and solar makes total financial sense. The payback periods are getting shorter and shorter and shorter. I think it's on the order of about 6 years now, possibly towards 4 years. You start looking at other investments in the stock market, or even just, I'm not a financial person, but you start looking at these investments and you go, this is actually a pretty good return on investment for what you get. So you got to really start assuming that people eventually will put up solar. I mean, I love driving around here because you guys have tons and tons of solar on all these different buildings, on schools and on just things that you wouldn't think would necessarily need solar have it. And there's a lot, of course, houses and stuff that have it, and it's cool. It's like watching popping popcorn. Like you have the first early adopters, and then you kind of like, now we're like into the mainstream. The whole bag is popping. So yes.
What about reducing the load first through LED lighting?
You also have, yes, reducing customer load, which LED lighting is a very big one. CFL too. It's like we went from incandescent. CFL is quite a big drop, but the quality of the lighting. I know that there's people that are like, oh, this lighting quality is not that good. But then once you've gone to LED, LEDs are awesome. And you even have, I have Hue bulbs at my place, and they're tunable. So you can change it from like the daylight light to the warm night light or whatever. It's pretty cool. So having LED lighting is a very big reduction in load. Also, people looking at insulation, better insulating their houses, all kinds of stuff that helps reduce demand. And California is one of the more efficient areas, partly because we have the better weather. We don't have crazy cold or crazy hot in most of the areas. But reducing demand is also a really big part of that. So yes, in fact.
I think you're heading in this direction, but there was an announcement recently from community college in Costa County, where they're setting up, because they've got, like all the other community colleges, they've got extensive solar arrays on their parking lots and so forth, but they're also setting up a microgrid so that they've got their own energy storage local to the campus, and they're basically forming an energy island on the campus.
Foothill's doing that too.
Yeah.
Indiana.
So
So all these areas that used to be pretty high centers for the grid, depending on the college and if they have like labs and heavy use of power. But I know like I went to UCI and they were doing the same thing, not quite as in the beginning. They weren't doing. I mean, they just had a cogen setup, and we'll talk about cogen. Yeah, eventually you start looking at these microgrids. I think overall though, you want to stay connected to the grid because you get a nice stable frequency, and you're able to, if you don't have some mismatch between your storage and your generation and your load, you're able to take from the grid. But you're looking at things like this is going to reduce the utilities money, in terms of reduce the amount of money they get.
How much is it going to cost us to stay connected to the grid when we're not actually drawing anything yet over the year?
Exactly. So it's
that's going to change.
It's going to change. And last question.
You touched on sunsetting net metering.
Yeah.
And it appears that the utilities are putting out 15%. When you get to 15%, photovoltaics are going to be throttled. Germany's way beyond that right now. So are they employing these?
I haven't heard like a specific percentage for California. The only one that I've heard in the United States is Hawaii, and they actually have hit a similar threshold. I don't know the exact percentage, but they're actually not allowing any more connection to the grid for solar.
PG&E's already starting talking that right now.
Well, we'll talk a little bit about the load curves and why they may be justifying this in terms of stability, but I mean, eventually, you got, that's the thing is you got this utility mentality right now of, well, we got to just stop it. We can't have this much, but people are going to want to, and they have financial reason to do so. So and we'll talk a little bit at the end, I'll talk about what about disconnecting. But this mentality does need to change. They have to embrace this because this is just the way it's going. I mean, this is sometimes you walk into the future, sometimes you go kicking and screaming. But let's move on a little bit. We'll talk here about cogeneration. I think cogeneration for larger commercial and industrial customers, it's going to just become more cost effective. I mean, as time goes on, we're kind of in like a spiral in terms of the utility rates because you got people that are, well, it's getting more expensive. Oh, I'm going to put on solar, or I'm going to do the cogeneration in a big customer. And then suddenly the rest of the people that haven't done that pay more because there is still a cost to run the utility, to run the grid. And so you kind of have this spiraling effect of where more and more, as the rates rise, more and more people will start, these cogeneration things will become financially viable. So, and we'll talk a little bit about that at the end. But basically, this is actually already common where waste heat is needed a lot, like refineries and paper mills, where you have refineries need to be able to heat the feedstock and all that kind of stuff. So they actually have a cogeneration setup. They started doing that like in the late 90s, if not earlier, for some places. Again, they're trying to reduce both their demand fee and their amount of energy needed from the grid. I think for smaller commercial, I'm not exactly sure about residential, but for smaller commercial or industrial, having a high temperature fuel cell that runs off your natural gas line or biogas, I guess in the future, makes for a very compact and it's pretty quiet. Near our facility, we have bloom boxes and they're pretty quiet. They put out quite a bit of power for the whole campus where we're located. So having something like that, sort of technology-wise, will be pretty interesting. But the one thing I like to talk about here is this is at John Wayne Airport. They have a traditional reciprocating engine or several engines running off of natural gas. They actually use the waste heat for evaporative cooling for their air conditioning. So that's actually kind of something where they can actually use the heat for cooling. It's kind of cool. So they actually built this plant not necessarily because of cost of utility that they were originally paying. When they did this expansion, if you've ever flown into John Wayne, it used to be very cramped. They actually built this third terminal or bigger existing, next to existing terminal. And the problem was their switch yard to Southern California Edison was right there. And it was a large one because they actually took power at a higher voltage. And as a commercial customer, the higher voltage you go, the cheaper it is because you own more of the equipment to bring it to you. So when you're reducing the size of your substation that they need, the cost went like way up. And they were like, when they were designing, planning it, they're like, oh my God, this is going to cost us a fortune. Well, they actually ended up going with they made their own little central utility plant, and it actually provides for most of their terminal load. I think it's in the 90s percentile. And they have a smaller connection to the grid, but they've reduced their load as seen by Edison and by us by most of it. I think still the airport operations, the tower and all that stuff is on a separate feed, but they reduced their demand from the utility because the costs are just they're going to be way too high by switching to a smaller substation. So it has nothing to do with greenness or anything, but it actually worked out quite well for them. But let's go ahead and talk about the load patterns, and we'll kind of get into why they're trying to stop solar customers and stuff like that. But old world, we'll talk about old world.
Not word.
Oh no! Oh man, it's not on the other one. Shoot, I go through this so much before you.
That'd be one
I'm
mistake.
human.
Come on. Your spell checker wouldn't catch it.
I wouldn't know that was horrible spelling. Anyway, so old world load patterns, they're mainly dominated by weather. That's been the case pretty much most of the time. You have cold climates, like the eastern seaboard, or New England, or even up in like Washington and Oregon. They're actually winter peaking, so they peak in the middle of the winter at around 9 a.m. Where like Southern California, you get Desert Southwest, Texas, those are summer peaking, and so they actually, the air conditioner load dominates in that case. And you're also influenced by time of day and day of week. So usually Monday, assuming that you don't have some weather thing happen in the middle of the week, Monday will be the highest. Well, with it slightly going down each day until Saturday and Sunday, which Saturday and Sunday are quite a bit lower. But right now, lowest is 4 a.m. around usually all the year, at least for Southern California. And, in other areas too, it's usually just before everybody starts waking up. The peak for summer is, they're peaking for summer, summer peaking is 4 p.m. in the summer and then 7 p.m. in the winter. And winter peaking systems, of course, at peak 9 a.m. and then weekend load is significantly lower. So as we kind of go to the new world with the overall system load's still dominated by weather, but now you have renewable generation. It's also dominated by the weather. So fortunately, wind and solar tend to be weathered in time opposites. So wind, when it's stormy, it's not sunning, and you got a lot of wind, and you've got a storm that has a lot of pressure differential, and you have a good amount of wind on the system. And then solar tends to peak during the high pressure, where the high pressure just comes over and sits on California. We have a beautiful summer day, and you have no wind. So they actually and then wind peaks at night. At least in our system, it peaks generally at night, and then solar peaks at midday. So they actually work. I call it sometimes like the dance of wind and solar, because they actually work pretty well against each other. Like they're opposites essentially. Of course, you do have challenges with ramping, reserve requirements, and timing of traditional generation to meet load. The accurate weather forecasting is going to be really vital, and we'll talk about ramping and reserve requirements. If you haven't seen this already, this is the duck curve. This is something the California ISO has put out. It's public. You can actually look at the document. They put out this load curve, and it basically shows, I wish they had the 2014 actual, I guess we're not at the 31st yet, but it might actually look a little different because we're actually heading towards the summer. We're already getting like characteristic of a summer load curve, which may skew this a little bit. They may have to show a different day, but you're looking at this and you're going, wow, that belly is getting bigger and bigger and bigger, getting fat, and there's nothing that's gonna, you just keep adding more and more solar, you're gonna have some problems where you've got a middle of the day is actually your lowest period of usage, which is something that's usually it was 4 a.m. And that's during non-summer months will be the lowest during midday. If you go on the California ISO website, there's actually today's outlook that will show the net generation or net load without the renewables, and starting to make that that belly. And sometimes the lowest period is middle of the day. So we're already starting, this is real. It's 2014, it's really happening. So in fact, we've seen things that are a little bit more aggressive than 14. You know, I've heard we may actually be ahead of this curve. So we must fill the bathtub, reduce the belly of the, you know, whatever you want to call it.
Shark data, weekend or weekday?
That is a weekday, I believe. I'm not sure if the 31st is. I guess they just show typical March 31st. March 31st, I guess it's usually the lowest or one of the lowest load periods. Spring is our lowest of the year.
But summertime, it's gonna be.
We'll talk about that. So
Totally.
they just finished up the current duck curve. So for non-summer months, you may have potential generation issues during the day. You're going to have a lot of traditional generation is going to, usually it tries to run as base load. It'll try to run at a certain output for most of the day, because starting up a plant for a big unit, we're talking on the order of hours. Some of the biggest units are like a day. So you have to plan this stuff way in advance. And now you've got things where they were starting up at 4 or 5 in the morning because they knew they were going to be needed all day. Well, now we need them on at night, we need them off during the middle of the day, and then on really hard at like 4 to like 9 p.m. And so you now got the start, stop. So that traditional, the transitional, the energy that I was talking about before with the traditional fossil, you've got a combined cycle that can ramp and do this. That's excellent. We definitely, that's nationwide or utility-wide. That is the way it's going for traditional resources, is to become more flexible for things like this. But that's still a really big reduction in load, and so we really need, essentially, we really need charging EVs. We really need workplace charging, I think, in a lot of ways. You need the appeal to reduce, or sorry, the appeal to increase demand in the middle of the day. Have people do laundry in the middle of the day. If people ever, it's kind of, I mean, there's different ways of filling that bathtub.
Sorry, let me ask a clarifying question. The problem with the duck curve is it's a ramp from the lowest point to the highest point. Is that the trouble?
There's several troubles. There's overgeneration where you have basically a very low loading level, and you're hitting into the plants that were designed to run as a base load where they don't actually change their output. And now you also have the increase in ramp. So that ramp in the afternoon is going to be very aggressive, where you've got to go from, it's like 12,000, 13,000 up to 26,000. You're doubling your load in like 2 hours. That's really hard. So, I mean, as there's actual operators that I know that actually control the units, or they do it through software, but they're actually calling on different units to start at different times. It's going to get more challenging for them in the future if we're going to be doing this kind of ramp. And there'll be solutions that won't make the duck curve so aggressive, but it's going to be challenging in the future to deal with that ramp. And that's also, we're seeing the effects of this through the time of use rate structure changes. They're changing that 10 a.m. to 2 p.m. on peak to like an afternoon on peak. So it doesn't quite line up, because 2 p.m. right on that duck curve is kind of like in the lowest portion. So I think it'll actually evolve over time, and it'll end up being, because the CPUC looks at this stuff too, and looks at the load, and they say, well, on peak is probably going to be about 4 p.m. till 10 p.m. or something like that in the future. I'm not exactly sure when that'll occur, but at least right now you can see that they are changing the structure for time of use. I'm sure there's people that have it. It's the EVA rate, or one of the rates that you guys have. That's, for time of use with EVs, change their structure. If you have solar, it actually has some financial impact. Both Edison and PG&E are doing it like at the exact same time. So yes.
Do you see, I mean, we have like really aging appliances, and I keep waiting for, I'd love to get one where I just say, there's a load of dishes in there, there's clothes in the dryer, run it whenever, I don't care.
Yeah.
Just make sure that's done by the end of the day.
I want to see it. I haven't really seen anything that is where we can call upon it. The only thing I've seen is air conditioner compressors that, like Edison has a pretty big thing where they can actually stop the air conditioner compressors in the summer. But I haven't really seen that much in terms of interactive appliances. And you start going, well, we need to like start working on this like now.
Well, they do in the east, they have electric water heaters that only come on at night.
Yeah, but most,
Right, but they're not triggered by a pricing, they need to have pricing signals and availability
Yeah.
signals in real
The
time.
other thing too is most of our water heaters here are gas. Yeah. So, because electricity here has been characteristically more expensive.
Can you clarify again? You're saying that net metering is not going to go away. It's just going to shift.
Well,
12 to 6 or 1 to 7.
Not that metering, time of use.
The time of use, time periods are gonna change over time. They already are for some rate cases, so they're gonna start shifting to match this, where, I hate to say it, but eventually you're gonna look at, so, you know, when solar's producing, that time frame is gonna be like your off-peak or super off.
That has a lot to do with which roof we put it on, though,
Exactly.
the way it's facing.
Yes.
It seems like energy storage is best for that solution.
Yeah.
Instead of 1,000 homes.
Yeah.
One energy storage.
Well, I think,
I
the west-facing roof still wins.
Yeah,
That's where the hard part is.
you start looking at people that are putting up solar in the future now are needing to put it not like south facing, but southwest facing. You do look at storage solutions. There are utility storage besides batteries. There is pump storage, and you can run that during the middle of the day to be able to deal with that load. But
Your solar depends on your orientation.
yes,
Your roof orientation.
Yeah. But I just kind of, you know, like it's kind of, you can see how it's gonna kind of happen though, is it's like we're gonna eventually need to start changing the pricing signals so people can interact better with the grid and stuff. So it's, and I know that pricing, especially like net metering, when people put up solar for certain use cases, and then now the financials change a little bit, it makes people unhappy. And it's very understandable. But this is just one curve. I have another curve I want to talk about too.
Energy storage, they're like putting meters on your thing to see that you don't shove more into the grid than you produce from solar with this SGIP stuff. If that's a problem, then why should they care? If I can, you know, sort of contribute as much as possible during the time when it's a problem, why do they want to limit how much people can actually shift with storage?
I don't know.
But you know what I'm talking about, right?
That is one area that frustrates me, because there's this kind of like, well, we don't want the consumers doing this or that, and it's like, well, it's gonna help you. I've seen some stuff where it's like,
right.
You know, unfortunately, it's, you know, again, this is just my opinion, but the utilities are trying to do one thing. I'm like, guys, you need to do something else. This is not, you're not gonna help your situation if you're gonna try and fight storage on the customer side, because they want to be able to have the power cheapest for them. And if it means that they don't give it to you and that they store it themselves and just use it later, then that's gonna, you know.
I think that's dangerous for the utilities to actually fight that, because the more they fight it, and with the cost of storage dropping, that at some point storage can get low enough to where some customers will say, hey, I can go off grid.
Yes.
And then what are they going to do that?
Well,
You can't do that because the worst case scenario, you have to gear yourself to the worst case scenario, which is winter time and lack of sun. And you'll find yourself out of power if you do that, if you make a mistake. You have
Well,
a big better way to do that.
yeah, so there's
I'm in that situation right now. I can have up to, I've had as much as 14 days with no electricity.
Wow.
So I have a backup generator.
Fortunately.
And I mean, there are people that actually have gone off grid with, you know, with usually off grid right now, or in the past has been because it costs too much to run the lines. If you have a really rural, it's like very rare in California, but in rural areas where they built a house out in the middle of nowhere, and they actually have solar, and they've done it where you do have a gas or some sort of generator backup. You have, unfortunately at the time, lead acid batteries, which aren't the best in terms of what we have available now. And
Propane backup is what
Propane is
everyone
better.
uses. Everyone where I am, a lot of people have propane backup generators. So when PG&E loses their lines during a big storm, we may be out for 3 or 4 days, typically in the winter at a time.
So
And
you really want that.
you have to have that generator to keep food frozen in the freezer.
Yeah, and so that may be, you know, a lot of, especially back east, I think it's quite common to have generator meals. They have power outages too that can be quite lengthy. And again, it becomes a safety issue of being able to have food and heat and being able to keep your house above freezing so that we don't freeze your pipes and all kinds of stuff like that. That it's very foreign to me in Southern California. But last question.
I'm just curious, how capable is the CPUC?
Oh, God, I can't. No way. That's a wrap. I don't know. To be honest,
I understand this stuff independently of the pressures from the utilities themselves.
I don't know. I'm not gonna, it's very political, and I'm here for technology-wise to show the technologies and stuff. Unfortunately, when it comes to the PUC, I can only basically offer what I think is sort of the future and the sort of the challenges. And
Any worse?
Any worse? Well, I actually want to move on to another curve that's a little bit different than the duck curve.
Summer curve.
The summer curve. So this actually this is public data from the ISO. This is part of, we have today's outlook, and then we have the daily renewables watch. So this is actually part of a PDF. You can go on their website. That's actually a really, really cool resource to look at what the wind and solar is doing.
It's a nice looking curve.
Whose website? Whose website?
It's caiso.com, and then you just click on the today's outlook, and then from there you can get to the renewables watch. So
There's an iOS app version.
there's an iOS version that gives you the real time, but the PDFs are really good for looking at the historic data. It's hourly. It is hourly average, so the curves are pretty similar, but just know that there is some granularity to the data. So it's not exactly this, because the wind actually can move around a lot more. It's very smoothed out here. But this is a typical summer load curve. This actually was the peak day, but summer load curves tend to look like this. And you can see the solar produces quite a bit, you know, of course, during the day, and it's actually helping reduce a lot of the on peak. So a lot of times, and unfortunately this is true with the ISO as well, as they show this curve and go, oh God, it's going to be horrible. But then you start looking at summer, and it's actually not too bad. So we do have issues in the winter and in the spring, especially with low loading. But in the summer, solar does really work really well for this. And it actually tends to kind of push the peak out later to like 6 p.m. And it kind of, you have a smoothing effect on the daytime usage. I mean, you're reducing a lot of the peak, you know, peaker plants are going to be running during the day to be able to manage this. And you know, the solar curve is pretty smooth, assuming you don't have lots of clouds, which in the summer you tend not to. So there's, you know, that is one thing with the duck curve that people get all, you know, oh my gosh, it's going to cause overgeneration. And it actually, you know, there is issue, but there is the summer, and I think that really does, you know, hey, that's really where our load is the highest, and that's when we really need the generation, and it's there. So yes.
You see in the bottom chart, which is wind and solar. When you're talking solar, you're talking like utility solar?
All utility side.
Okay.
So
There's really no, is there other estimates anywhere of what the total residential solar?
It's on the order of, I don't have like an exact figure, but it's on the order of like 1,000 to 3,000 megawatts, somewhere in there. Unfortunately, we don't have an exact number.
Well, all they know is what's approved. They have no idea what all our houses are generating on a regular basis.
I mean, there's stuff like Enphase has their, you can look at it and stuff, and it'd be cool to get like an aggregate from that.
Does anybody, there's nobody that collects data, does some random sampling or something like that? I think you can get sampling for anything like Nielsen TV or something. It's like there's a market or something to say, well, how much solar is actually being generated that's not being metered?
Right.
Yeah,
well, it's subtractive metering, but it's just less than.
Yeah, so we see it as a reduction in load.
Yeah.
So in fact, when you see clouds come over Southern California, load goes up.
You can see that.
Mm-hmm. Yeah, it's real. It's real now. We didn't used to, but it's become more commonplace. It's something we can see. You know, so that's something to at least be, it's noted.
Yeah, and
we'll talk about solar eclipses too as well.
I know with Enphase, you have the ability, at least Enphase it collects all this data every 5 minutes. They get data from every unit.
Yeah.
And they can that they can change the software in their units.
Yes.
I think they did
They did
here
for
a couple of
Hawaii.
months ago, they did 800,000 units in one day.
Yeah, they did it for Hawaii. There
Yeah.
are certain standards that are set for grid or the grid tie inverters, basically frequency and voltage considerations. They want to be able, if the grid starts going either really high or really low, really low, they actually want to, I guess, disconnect. And of course, when you start getting to over generation, they also disconnect. But Hawaii, the band that they're in is set pretty narrow, but Hawaii wanted it widened so that way they didn't have such big load swings. Hawaii is kind of a unique case because they're an island nation with a lot of actually oil generation. So they have oil plants that they're run like a traditional steam plant, but they also have wind and they have a lot of customer solar generation. I think it's 12% on how much they have right now. And they're looking at like over generation, but they don't have a national grid to feed it into. They don't have neighbors for them to feed into. So when they hit a time when it's like they're serious over generation or under generation, and you're having these crazy load swings, you're jeopardizing reliability. So that's part of the reason why they're no longer allowing more solar, because they essentially need storage really badly to be able to handle more, because of the way how they are an island or a series of islands for their load.
They're ultimate microgrids.
Yes, yeah, ultimate microgrids there. So it's, yes.
You mentioned it just a couple of minutes ago, solar eclipse. Yesterday, Europe had a big eclipse. How did they weather it? Because most of Central Europe, Germany, was in the midday. How did they survive?
So from what I've heard, they did survive. They survived partly because they had cloud cover, so they already had other generation online. I believe it's around 13,000 megawatts they lost for a time frame. For that time frame, it went down by 13,000, and then eventually came back. You know, like I think their order is like 2 hours or so for the whole, or 3 hours for the total reduction to major eclipse to being out of it again, somewhere on that order. I haven't talked yet to the guy at the ISO that I like to talk to about this stuff, who really follows it really closely, since it just happened yesterday. So, but from what I've heard, they did survive it. We have one in August of 2017. And the big difference between us and them is that it'll happen in August, so we're less likely to have cloud cover. Germany has a tremendous amount of solar resources, but their total solar, like the amount of sun that hits their area is like on the order of like Alaska in terms of light. So they have a lot of extra resources that aren't necessarily producing as much. The capacity factor is what that's called. So we have a higher capacity for solar in terms of how much we're going to be relying upon solar or using of that solar during that time. And you start, it's looking to be a big challenge, but luckily we know look at a farmer's almanac and you can find the exact times. So we're basically, the other thing too is the good side of it is it's going to be August and you're going to have a lot of units on anyway because it's the summer, so you need them all on. So they'll be all there and ready kind of to be able to take over. So there'll be a lot of planning, and there's actually, we're talking more about looking at standards. That's because now, before it was like, oh, solar eclipse cool, it's not. So looking at standards in the future that go, okay, well, we need to look at when the next solar eclipses are coming, and that way we know, many years in advance what to do. So Germany, though, was a good dress rehearsal for us to see basically how a large-scale utility is going to handle it, and I think they did pretty well. You see blips here and there in the utility sphere, but I haven't seen like a full-on analysis of the data yet. So
next time you come back, you can give us.
Next time I come back, and that solar keeps growing like crazy. I mean, when I started at the ISO, it was under 1,000, and in the time since, it's I think.
How long?
I started in 2012, July of 2012, and in training, and then now I've been there. It's almost going to be 3 years, and we're already like an order of magnitude higher. So when we started, it was on the 5,600. Now it's like 5,800 peak.
So now here's the question. How's global warming going to impact that?
Well, assuming it's going to be climate change, two things. First, I'll talk about increase in storms. You're going to have damage to power lines. You're going to have damage to utility assets that are going to take longer to repair. So you have things like having customer storage or customer generation where they can actually provide for their own load for a longer period of time. You're also looking, I mean, if it's going to be hotter, you're going to have more air conditioner use, but also humidity. Humans don't like to be in humid areas. Florida was being an exception, I guess. But we run the air conditioner a lot, even just for humidity reasons and stuff. We do run it through heat too, but like we want to make sure we have good air for that. And so as you get into, say, a humider area, when it wasn't as humid before, you're going to have more air conditioner use because of that. So, and you do have things like weather patterns that are changing faster. So more of doing the analysis of the weather and what's going to be predicted. It's going to be hard, but we're just going to have to do that, right? So.
What kind of pump capacity do you have for storage capacity pump?
Can't talk about all the specifics, but PG&E, this is public information for PG&E. It's got a unit called Helms. It's got 300 megawatt Francis turbines that can be run, so 900 megawatts of pumping power. But again, when you look at the duct curve, that's way more than what we need. So in fact, unfortunately, because of the time scale, it's like I haven't heard anything about building a new pump storage facility, so we would need that started now. So,
Is that Lake Castaic down south?
it's near Fresno.
Fresno.
Yeah, I should
Big
know.
ones are Thermal Lee, Colorado, and San Luis Reservoir.
Yeah.
Those are the two biggies.
Okay, yeah, so there are pumps, and there's water pumps that are pumping water for Southern California from here that are actually, they were on a demand response sort of program, and like they could, I think I don't know if it's called public, but there's pumps that could be used for that, that could be used for demand response and stuff. But again, it's on the order of like hundreds of megawatts for current storage just for the traditional pumped hydro. We need thousands, and so, the reason why I kind of like go where a lot of this customer storage is because storage right now, I mean, prices are coming down, but it's still expensive. And I think overall, like you're looking at things like, well, if it's still expensive or relatively expensive, you want it to make the most money. Where's energy in terms of electricity the most expensive? At the customer site. So you want to be able to maximize the return. You're going to look at things where, utility pays very, relatively less for electricity than the consumer, so that way they can sell it on to them. So if you're going to have more expensive electricity, then you need to, you want to be able to store it and capture it where it's.
Are you talking about residential customers here?
Yeah, residential or commercial.
Or commercial, industrial?
Yeah, because sometimes their demand fees can be very expensive, a good portion of their bill. So, yes.
Another difference between the old world and the new world thing that occurs to me is the old world control of generation and usage was centralized, whereas you're moving to a more distributed control situation where in your transmission you have the different
different unit things that control the transmission, like
transmission, but these are controlled over long distances.
Yeah.
And I'm wondering, all these different industrial control systems that are controlled remotely, are the new installations that are being planned for all these have more security built into them?
Security.
Yeah, there is a lot of, there's standards actually built for security in terms of what, I don't unfortunately know the details of like how they do the security, but I know there's encryption when it comes to control links between California ISO actually manages like the grid. They manage the dispatch of generators, so a lot of this is very automated, or there's usually like a collection of resources that are say owned by companies. There's like a company called Calpine that manages, they have a lot of peaker plants and stuff like that. So they have we contact them if we have to do something exceptional outside of the automation and market processes that we have. But a lot of this stuff, it's very well encrypted, and they have certain security measures that have to be followed due to, there's federal regulations that are part of that. So I know that there's quite a bit of security that goes into it. There's certain, ways that they control the generators. It's usually like there's a link between them it's all encrypted, and it's just, we're constantly pinging them back and forth to get data from them within, on the order of like 100 milliseconds.
And do these new remote transmission control systems, do they introduce any more transmission losses than?
Well, like I know with like the phase shifting transformer, you do have a small, you do have a small amount of loss, but it's pretty small. So let's see if I can just.
The phase shifting transformers, they do voltage tap changing as well as phase shifting?
I don't think, well.
Or you have two
actually, you would have, most of the time on the transmission level, you have voltage considerations that are done with other equipment. They're actually like capacitors, shunt capacitors, and shunt reactors that control voltage. You also have generation where they have, if you know much about like VARs and stuff like that, they'll actually boost or buck VARs, which cause
they'll do it from the generator itself.
They'll do some for the generator itself. It depends heavily on the line that like where is the voltage low or high, and what generation is around their own line already, because increasing VARs or decreasing VARs it's a reactive, it's not a real power. So actually increasing it doesn't, it has a very, very small, that you have to take real power to make the reactive, but it's very, very small. So it doesn't actually affect the generator's cost, and excess fuel use or anything like that, unless they have to be online for voltage concerns. Then you're looking at, you have to pay them to do that. So, but if they're already online and stuff, you have things like that. But that sort of stuff is actually done by the transmission owners and operators themselves, not the ISO. Like we manage and monitor, but that's something that they have to really, they have equipment that does that for them.
Can you define that as a VAR?
A VAR, so power flow or AC power can be thought of kind of in if you take a wheelbarrow and you're walking with it, you have to lift it to move it forward. VARs are a lot like the reactive. VARs are the lifting motion that gives you the ability to move the real power, because VARs are actually used by transformers to transfer the power. And a VAR is basically an out of phase current with respect to the voltage. So, but basically you can kind of think of AC power as a wheelbarrow where you have to lift it in order to move it forward. Moving
So
forward
it's like
is the real power.
building up momentum for a change.
It's
lead and lag. Lead and lag, the current in AC systems, the current can lead or lag the voltage.
Yes.
Or be in phase with the voltage. If it's leading or lagging, that can add a phony load, you might say.
Yeah,
and it looks like it's a heavier load than it actually is for the transmission equipment.
Right. So when you have a lagging load or a leading load, your current is going to be out of phase with your voltage, and so you no longer have just like a resistive load. So a motor is actually lagging, and you have to. And a lot of the load on the system is a motor load. Lights are a notable exception, but you have things like air conditioner compressors, pumps, and all kinds of stuff like that that are actually a motor. And so they have this lagging power factor where their voltage leads the current, or the current lags behind the voltage. And what ends up happening is if you look at the instantaneous voltage and current, you actually have like periods where you're using very little real power, but you're moving a lot of current along the lines, and so you have losses. And that leads to tends to lead to a voltage drop as well. So when you start having this voltage drop, now you're drawing even more current, and so it's not a good situation. So you have things like capacitors. Capacitors act as they lead, the current leads the voltage, so you actually are able to correct.
Adjust it.
There's actually a whole subset of power factor correction, which again, this is all kind of this is all standard like normal power system. This will all still exist. You will move towards like variable frequency drives where they actually have capacitors internally that are able to, they'll take the power as a resistance, just right in phase with the voltage, but then they'll use the capacitors and stuff to make their own variable frequency, and they're able to provide the reaction power that way. But when you're a customer, not typically for residential, but for commercial, you actually have to have power factor correction, or you have to manage your power factor, because if you lag too much, the utility charges you, because you're just essentially drawing more current than you're giving it back at every half cycle, but then you're heating up the lines more, and you're not actually producing usable work from that.
I know in these inverters that are solar inverters that are sitting on roofs all over the place, like the Enphase ones, they have the capability, the technical capability of providing leading or lagging.
Yes.
But they don't at the present time. They're set up to be just power factor of 1.
Yeah.
Is there they can do it. I mean, if somebody said, hey, can you give us, if somebody will give us the command, we'll do it.
Okay, yeah, that is something that should be considered in the future, that really currently isn't being done. Everything is like just 1-to-1.
Yeah.
And I'm not exactly sure why they haven't really pursued this, but it should definitely be something in the future that they.
Isn't that what's proposed, Rule 21?
So there you go. They're I don't follow all the different proposals and stuff, but they
right now.
Yeah, so they are working on it right now, and some of these, especially with Enphase, the updates are right over the internet, and they could totally change that and have it be able to be a very useful source. So I think, in overall, when it comes to like the reactive power stuff like that, you're really, for commercial, it's quite important, and for residential, I think more of your load is non-motor, so then it's, I guess, maybe not as important, but it depends too on the structure of the distribution and how that works. But it is very fascinating. That's in development right now. So any other questions? Or yes.
So in this whole talk, you have assumed that in California, all the hot water heating and the domestic heating will be done through natural gas. But I think as global warming progresses, will probably go off natural gas, and all that will be transferred to electric. So is that, I also think.
Well, I don't think it'll be this quickly. I mean, because like I think there's things like either solar hot water, or you're looking at like the heat pump hot water heater, which is, where you're basically using the room heat and putting it into the water. It's awesome. I'm glad that they exist. And I'm hopeful that more people will install them. But you're starting with an energy source that's more expensive, and you're starting with a capital cost. So people need, when it comes to something like that, I don't see that change from going from natural gas to electricity happening this quickly, because you have things like, at least especially in Southern California, we run the heat so little, and natural gas is substantially cheaper per BTU than electricity. Or sorry, the gas is much cheaper per BTU than electricity. And you're looking at a capital cost, and people don't pay it. So, I mean, you have to have an incentive.
But you'll probably have a carbon cost, right?
Right. So there will be incentive, but I don't. It will take a long time, because you got things like the place I currently own, or rent actually. Sorry, it doesn't. There's like the electrical service couldn't handle what you're describing. So it barely handles my car. So you'll have things like that won't change, and so people will just be burdened with the cost of the carbon tax. So I'm not sure, at least in California, heating is quite a bit lower usage than air conditioning, so I don't think people will be changing from electric to natural gas, or sorry, from gas to electric very quickly. I don't think in the terms of this scale. Over long term though, eventually I think, yeah, we will. I hope that the gas system, I think the gas system has a very important place. And I think biogas, or moving towards having basically processed methane from biogas sources being used in the natural gas grid is pretty much the way forward, because especially for cooking, I love cooking with natural gas or with propane or whatever, with gas, it's a very good source. And then for heating, basically for any heating, natural gas or, biogas kind of source, they work really well. And so it's going to be hard to transition to an all-electric grid. I'm not sure that will be maybe long term in the future, but we have this asset of natural gas, the pipelines and the piping available to the houses and the metering and all kinds of, very high sunk cost in that. So I think, suddenly just going out, we don't need it anymore. That's not going to, or, over time, just getting it away is not really going to happen. I think they'll probably move to more of like a renewable natural gas, essentially move to a biogas. So
with heat pump, at least heat pump water heating is, I think, very practical if you're on propane.
Okay.
I happen to be on propane and I switched over.
Okay.
And my 4.5 kilowatt electric heater is now a 650 watt heat pump.
Okay.
And so it was,
awesome.
and when you're paying, we were paying last year $4.15 a gallon for propane. So it was more expensive to use propane than electric heat.
Yeah, so there are areas of California or, a lot of areas of the country that don't have natural gas, because natural gas is usually substantially cheaper than propane. Yeah. But for propane areas, heat pump water heaters will probably make a lot of sense. And then you're looking at things like, heat pumps for your house too. But I think natural gas will still have its use like in the generator, for your backup generator and for cooking. I think it'll still be common. There are alternatives, of course, and there still are all electric houses, but I think overall we're still going to see natural gas for a long time. Not on the scale of this sort of problem.
Well, not only that, but if you're not going to allow you to put solar back to the grid.
Yeah.
I put all the solar in my house, generate during the day, then I'll just have a natural gas generator
for
nighttime.
Yeah.
And then I can lop off the grid.
Yeah. Well, I think a lot of the storage and the customer generation and even all the different technologies I mentioned in the transmission grid management, there'll be solutions for each case. So there won't be one size. If you can get anything out of this presentation, there isn't one magical technology that solves all the problems that we're going to have, but there are different solutions for different subsets of the problems that we have. Yes.
You talk about the blown energy fuel cell thing for home generation or
for small commercial.
Yeah. So is that more reliable? I mean, in automotive use, they said these membrane fuel cells, after 1,000 cycles, you got to get new membranes. Are they more reliable in that kind of a?
I don't quite know the reliability, but I do know it's a different technology than in the cars, because the cars are using hydrogen as their feedstock or their fuel, and Blue boxes use natural gas, and they actually have they're a different type of fuel cell. It's like a high temperature, it's like solid oxide, so I think it's almost like a ceramic style.
What's the maintenance interval on how long?
Unfortunately, I don't quite know what the maintenance interval is for all those, but I do know that there are areas where they have them and they've been successful, but it may be that they're expensive and they need more research. But I've seen they're doing good as a company, so hopefully overall it makes financial sense for some customers.
They had said they were going to come out with a home version of their Bloom box.
Yeah, and I'm not sure.
That's not for years.
Yeah, not for years. It may be that because a lot of commercial entities have higher, they have either the higher demand fees or they're in their rate structure makes more sense for commercial usage, but also the fuel cells I've seen, they're pretty large and they do make a fair amount of, noise. So, when I say the commercial side, it's, smaller than an engine room with a natural gas generator and all the associated equipment with that. But it's smaller than that, but it's probably not to the hot water heater size yet.
I would have to say that they don't make financial sense,
okay,
but they do with the California self-generation incentives and the federal incentives.
Okay.
So once you kick these in, they start making sense.
Okay.
But basically, they're using our tax dollars to make sense.
Okay, well,
Dollars to make sense.
but ideally with tax dollars and that kind of stuff, just like how electric cars kind of have tax incentives and stuff that make it more financially palatable, you need early adopters that are willing to.
Is that any different than the gas industry with subsidization?
Yeah, there are subsidies and things to basically kind of get ideas moving, and sometimes people think that they shouldn't be there or that they're misplaced, and for some that I agree, it's true, but I mean, there's cases where it's like we need adoption of this to see, like you're saying, well, is it gonna wear out? Is it, there's lab tests you can do, there's lab scale ones you can do, or you can have a small commercial one, but eventually it's gotta go from the research lab to the real world and see what the real world problems are. So the incentives allow that to happen. Hopefully that eventually, though, that they become inexpensive enough and reliable enough that they don't need those incentives.
Well, I think one measure of Bloom is the fact that if they were that successful, they would have gone IPO already, because they've been around 15 years, and they've I know people that work there, and they've sort of rumored they're coming IPO, but they've never been able to because they can't make any money.
Okay, well, I in this presentation, I kind of put things, I'm like, I think this will happen, but there are times where it's, hey, this is wrong. So it may not be that we have commercial storage in that form, or sorry, commercial generation in that form. It may just be solar.
No, it will come. It will come.
It will come. Okay.
And the tax dollars do help.
Okay, good.
I think they will.
Yes.
But the company called Fuel Cells putting multi-megawatt units out now. The solid oxides are running at about 180 degrees.
Okay.
That's the temperature rating.
No, solid oxides run.
They're really high.
Well, some of them are 180.
We're talking about membranes.
Yeah, for fuel cells, there's quite a different number of technologies and fuel stocks you can start with. The hydrogen ones where they're much lower temperature and stuff that they've been pushing for automotive use, but
they're called proton exchange membrane.
Oh, okay. Yeah, I'm not a fuel cell expert, unfortunately. I find the solid oxide just seems like that because you're starting with a higher temperature, you can use that waste heat, and then you can use the electricity generated from it. And I think overall, when it comes to technologies of the future, the lower the maintenance and the lower the moving parts, the more reliable it is, and the more likely it's going to remain around for a lot longer. So things like solar panels that need occasional cleaning, and that's it. And you do have inverters, but they are solid state, and they're working on increasing longevity to crazy levels, especially with the microinverters. So I think overall, when you look at something like going to a reciprocating engine or gas turbine even, that's got maintenance, that's got people that need to come out and check on it all the time and stuff, and you look towards things like batteries that need quite a bit less maintenance, or that hopefully just in general, if you have something that doesn't have moving parts and that can be easily monitored remotely, that doesn't need somebody there coming on site a lot, you're looking at lower capital costs overall, and then you're looking at hopefully longer longevity. There's exceptions, of course, but overall, I think that's kind of the way to think.
I was going to mention the batteries on batteries. I think Tesla right now today is paying about $180 a kilowatt for their batteries for their vehicles, and with the new battery plant, they're going to be under $100, right about $100.
Yeah, that's awesome
per kilowatt. And I know that some, at least for Aquion, they're selling right now at about $350 or no, $500 a watt. Or kilowatt. They expect to be 350 by the end of this year. And they were talking about before 2020 down to under $200 a kilowatt. And those batteries theoretically have a 20 to 30 year life.
Yeah.
Think about a leaf pack at $50 a kilowatt.
Yeah, I know, right?
Leaf pack.
They use leaf packs because there actually is. I know there's a guy in the Netherlands that actually has like 2 packs that he bought that were very inexpensive, and he has
cars.
Yeah, he has a full-on storage system already, and it's like you can think of it as that's not even a pilot. That's a commercial use of it because he is saving his energy that way. So
Right,
it's kind
he's
of
using the
cool.
Sunny Island inverter, which actually does exactly what we've been wanting for ages. So for those of us with SMA inverters, it's a great solution.
Yes. Yeah. So, and I know somebody that has an old N-Track, I think it's N-Trax or N-Trax. It's Xantrax. I'm sorry. Xantrax inverter that allows the same thing. And since it's a grandfathered installation with storage, they don't have to get
changes the batteries. Yeah.
Yeah, he just changes the batteries, and suddenly they're a lot more flexible because those are
The
all
Sunny
massive.
Island is, the Sunny Island is interesting because it will actually send a serial signal to your SMA inverters that are grid tie inverters to let them run in island mode when the grid is gone.
That's awesome.
And so that's actually something that most grid tie inverters won't do.
Yes, because
Sunny Island will isolate them and maintain your pack.
yeah, that's pretty awesome. And I know he somehow, well, I think he ran his own BMS and then was able.
He did his own BMS, and that's the piece that's kind of the missing piece. But I'd love to see people gel that into something that, you know, ideally you just get something and then make up connectors where you just take a leaf pack and jam a connector in the end of it and have a Kickstarter project or something for the BMS.
Yeah, so we'll see where that ends up. But I think that's again with the EV packs. I think there's a lot of promise because they are inexpensive to start with, and your requirements are
seeing a lot of them available.
Yes.
Are there any issues or limits to driving transformers backwards? Like on the pole behind my house, there's a transformer that's taking the high voltage at the top of the pole down to the neighborhood voltage.
Yeah.
Now, if it starts running backwards and pushing power into the high voltage, maybe I can grasp that. Now, wherever that high voltage came from, can it be driven backwards? I mean, is there any limit in this?
There are a little bit of concern with if you start driving it all the way back. Say if you have because usually with a neighborhood system, like what you were saying, you have like 5 houses or houses connected to there's one transformer on this side, then there's another transformer. They're all kind of on this like low voltage network. So the first thing is when you push power out, it just goes right
to your neighbors.
But then if you have say all your neighbors are awesome and everybody's pushing back, then yeah, you start looking at the power is flowing backwards, and there's no reason why it couldn't. You should be able to push. I imagine that. I mean, I don't think they were really tested in the past to be able to push all the power backwards, but I think you should be okay. But the one thing is when you start getting up to the distribution level and start having lines that are going backwards, you have things like faults and stuff where it was flowing backwards, and then now it's said like you have a fault on the system, and it's not clear if the protection system for that line is looking at the feeder breaker, and the feeder breaker's just shows the current is flowing back into it, and then all of a sudden the back end current goes way down, but it's still feeding, and it's not below the fault level that would normally trip the line. Then you start looking at then the system protection needs to be evaluated. But I've talked to a few system protection engineers about whether when you start looking at the line, if you've got tons and tons of customers that are just pushing the line backwards, I believe the fault current, where you basically have a line on the ground or something, the inverters aren't able to feed into that due to the voltage. They don't have any spinning inertia where they can just provide fault current for a certain number of cycles. So they'll actually just trip out really fast. But I think overall you start looking at it could probably be more of a concern of the distribution system protection, because you can maybe have issues with it there. But the actual transformers that are just at your house, I think the only issue is possible overheating, because now you're pushing out during the day and you're taking it at night and you're changing the heating patterns of the device. So they're meant to be air cooled in the middle of the night, essentially, to shed any of the heat during the day. And if you're suddenly taking power at night, late at night or something, then that changes the cooling patterns and you may reduce the life of it. But there is concern the distribution grid, whether you're going to have system protection issues, but I'm not sure that I don't know that it's been tested at the level that I think it'll eventually go to, but it may end up being okay. We'll see.
So today, do we ever see substations?
I'm sorry?
Today, do we ever see energy being pushed back to the substation?
Well, unfortunately, I work at a level that's higher than the local substations in terms of looking at the power flows, but I don't think we're at the level that they're actually pushing back in. I think it's just still major reduction in current during certain times of the day. But yeah, so, but eventually we will, and it'll be interesting to see the studies and stuff of how that'll happen and how it can be managed.
Since we have a fresh water problem, has there ever been a consideration of using saltwater ponds for pump stations back and forth from the sea?
I haven't heard anything about that, but usually for pump storage, you want a high level of, it's called head in the dam world, of where you want the dam world, and so you want a high level. You basically, it's almost kind of like an analogy with electricity. Electricity is actually, they use water analogy, but you want a differential. You want a big difference between the low level and the high level. And so if you have something like usually like the sea, it's usually those kind of seas that are very short levels. So you need to be able to have the water fall a long distance, so it gets a lot of momentum behind it to be able to spin the turbines.
What's the minimum height?
That goes kind of into the theory, the dam theory about this, but it's like there's different designs depending upon if you have low differential and higher differential. They change the type of turbines. They go from like a Francis turbine to what's called an impulse turbine, where they actually spray a jet onto like a paddle wheel thing. And that's kind of like out of my scope, but they do have different designs depending upon the height difference. But I think overall they want to have the maximum height difference with the maximum amount of water to be able to move back and forth.
I think
Especially
you make a comment on that. The higher the difference, the less water you have to move. So your civil structure gets smaller with a higher differential height. So ideally, you'd like to have take the water, pump it from the ocean to the top of Mount Everest and run back.
Because you're using gravity.
Yeah, using gravity. But the problem is you need 2 reservoirs for a pumped hydro system, and
You can
that's
get away with one if the sea is the other side.
yes, but I want you to get the environmentalists to say, okay, to you taking a million tons or a couple million tons a day of salt water, pumping it in high into the Sierras and putting it into a huge valley, filling the valley with salt water, and then running it back and forth every day.
Right. So there's several environmental problems with that. You have not only there's requirements where you can't take from the ocean. There's actually power plants right now where it's called once-through cooling, where you have power plants that are built on the coast. They're not allowed to use the ocean water past 2020. They actually have to use the air. So that's been a big deal. So you're not
Diablo Canyon?
They're exempt, I believe, till 2024. but there was that was part of San Onofre when San Onofre was shut down because of the steam generators. We're still going through things like that, so I got to be delicate here. But basically, they would have also had to convert to like a traditional evaporative or some sort of air cooling, and that's a very large expense looming on the horizon for them. So that's. But there's other power plants along the coast that you can't use. You can't use the ocean, and so to do pump storage using the ocean is not going to happen.
That was the whole idea of placing it there, right?
It was.
Yes.
But just 2 other things too. Salt water is incredibly corrosive. So when you start trying to pump it through things, it's really bad. It's corrosive to everything. So and also, whatever reservoir on the top, you're totally salting the earth. So those are 3 reasons why that's going to happen now. But there is actually a desalination plant in Carlsbad that's being built that will, with this sort of duck curve, they can easily run during the
run it in the middle of the afternoon.
Middle of the afternoon, it's perfect. So yeah,
let's build more.
Exactly, and there is talk about building more.
They're really expensive.
They're really expensive, and the other thing too was they were trying to build them when it was drought season, and then I think right as they start to go, okay, fine, we'll build it. It gets rainy, and then like they stop building because they go, oh, it's where drought is over. And the politics say that we don't need it anymore or whatever. So but now it's being built. This Carlsbad one, it's in the middle of construction, and they're going to use the waste heat from a power plant that's nearby for the heating the water to do the process. So it's looking really promising.
Oh, they're going to be cogeneration then.
Yes, cogeneration, yeah.
So with hydro being such a big renewable source in California, does the drought impact your ability to use that at all? Or is
Yes.
it still- okay.
So the other thing too is the renewable portfolio standards in California don't count large hydro.
They don't, because it's a separate category, but I'm saying, is that at risk now with less water?
It's a concern. I haven't really seen, because like I believe was it last year, they were doing a lot. We do studies every year on like the summer conditions and what the summer electricity demands will be like. And that includes not only the hydro where your loss of generation, but also pumping more water to be able to serve the needs of California. But we do studies every year for winter and summer. So that's something they look at all the time to see what kind of output they're going to get. And, it will be reduced, yeah.
Isn't California's renewable portfolio for water coming, don't we include the stuff from Oregon and Washington? Because we don't really have much to speak of.
You mean for renewable sources?
Yes, for the hydro.
Oh, for hydro. Well, we don't include any large hydroelectric inside the state or outside.
Categorized separately.
Oh, it is categorized.
Yes, renewables count in California doesn't include it because otherwise we'd be way over targeted just from the large scale hydro.
Yeah, well that, and then also, it is true we would be over target, but then also you could have 2020 be a drought year and the utilities be like, hey, it's a drought year. How are we supposed to use the hydro? So I think they kind of exclude it too because they go, now you can, you don't have the ability to have the weather kind of be the reason why you wouldn't be able to make it essentially. But the small hydro, anything I think under 50 megawatts or a run of the river where it doesn't use a dam, it's just a turbine in like a narrow part of a river, does count, but it's pretty small. You can see on the Cal ISO website, they show it. It's like 200 megawatts. So yeah, and there's other sources of renewable energy that do come into the grid. They're considered imports in a lot of the ISO stuff, but there is stuff that's outside the ISO boundary that comes into California that's part of theirs. But I believe the incentive is to build it here. So especially for like solar, we already have crazy resource that's available for us. So yeah.
Okay. Did you get through all your slides?
Yes, I did. I had so many questions, but
We have a general sense of how, with all these changes in renewable energy and whatever, how the carbon emissions of electricity are changing.
Well, there's also standards for that too. So there's they have to reduce to 1990 levels as well. So in terms of overall, I think that's not only electricity, but I think there might be other sectors. I'm not sure about that standard too much, but yeah, there are.
As the time varies during the day, like.
Oh.
Like if I'm charging at night, is it lower carbon than during the day, or how's that?
Well, I mean, ideally, because electricity prices are going to cause generators that are, say, inefficient, so heavy carbon producers will reduce or shut down during times when it's not cost effective to run them. So ideally, you're looking at having the cheaper cost is probably going to have less carbon in it. Because late at night, you're going to either have wind or you're going to have base load, which base load's pretty efficient. It's meant to be run all the time, and it's tuned very, very well. And the other thing too is California has emission standards for power plants. So there are things like you can't start and stop the unit a certain number of times a day. You have to. There's like a minimum on time, so they can't just produce. Because they're kind of like a car too. They produce their worst emissions when they're first starting up. But once they're running, there's like a minimum on time because like, hey, you started it. They had a minimum start amount, and then now you have to run it for a certain amount of time. This is all taken care of in the market or by the operators. There's things that we keep track of for them because otherwise we don't want to have a unit come on and be like, oh, hey, we needed that unit. Oh, well, you can't turn it off. That's not good. So we have the ability to manage that. And so we don't quite look at carbon emissions throughout the day or stuff, but I mean, if you're going to have higher load, you're probably going to have higher carbon content because you're going to have summertime loading where you got that peak that's substantially higher. You're going to have a lot of peaker plants, and you're going to have things that just power plants on in general to handle that load. So you're going to have more carbon. So higher loading, probably higher carbon. So don't charge your car like at 4 p.m. on a hot summer day, which most people probably aren't doing. So, yeah.
Huh.
I think we ran out of time.
Thank you, Jeremy.
Thank you, Jeremy.
Great job.
Very interactive.
And then my camera died on me.
Still need cars for mission.
Okay, good.
Thank you all for coming.
Oh, wait, I gotta say something.
Drive you days. So,
In fact, I went to TGVA.
I got some clearance shirts in the back. I'll take whatever you want to offer for any of them. They're various sizes. Our old design and the one you're wearing, the green one.
What did they say on it?
That's from the major event, the rally. Not the one this September, but the previous September. So I've got those in small and extra large, and then I have our old logo ones in medium. Take whatever you want to offer. Sorry.